In this video, I will clarify the dynamics of the Easter Island model. As a reminder, time is continuous and there are two stocks influencing each other's growth rate. The stock of resources S, forests, soil, fish, birds, and the population L. To find the steady state of the whole system, we will have to find an equilibrium for both population L and resources S that are stable. Here we start with the resource dynamics. So the natural growth rate of the resource stock is logistic. It is G of S equals RS 1 minus S over K. R is the regeneration rate, which is assumed to be relatively slow on the island since palm trees take a long time to reach maturity. K is the carrying capacity of the island. It is the maximum value of S possible, which is reached when there is no harvesting. As a reminder, S dot is the time derivative of S, so it is ds over dt. The law of motion is simply the change of a variable over time. Here the net growth of S is the natural growth rate minus harvesting. We may substitute G of S and H, which we already derived, and find that we can have a simpler equation, where S dot is a function of two stocks, S and L, and of the other model's parameters. The first S implies that more resources make the stock grow, but inside the parenthesis, we see that more resources actually bring S closer to the carrying capacity and also increase the effectiveness of harvesting alpha beta SL. In the Lotka-Volterra model, resources here are the prey. As always, we denote the steady states by a star. Since S dot is a product of two factors, if either factor is 0, then S dot equals 0 and S is at steady state. The first steady state happens at S equals 0, which corresponds to a barren island. No nature exists, so nothing can grow. The second steady state corresponds to the inside of the parenthesis being 0. We call it the sustained island, where natural growth is exactly equal to harvesting. Since L is a variable, then there's an infinite potential combination of S star and L star that can make growth 0. For instance, if L star is large, then S star has to be small. This is because if more islanders harvest, then the natural growth rate of resources has to be higher to compensate. And this happens when the stock is smaller because it is farther from the carrying capacity. To pin down the exact value of S star and L star, we will have to introduce a new equation corresponding to the steady state of the population L star also. A last but very important consideration is what happens away from the steady state. For instance, what if the island is sustained, meaning that R minus R over K ST minus alpha beta LT equals 0, and then imagine that for some random reason L or S goes up. From the equation of S dot, we see that this would lead to S dot becoming negative, meaning that the stock would start to decrease, both because of extra harvesting or simply because the stock being too close to its natural carrying capacity. Similarly, if either L or S decreases, then S dot becomes positive, meaning that the resource stock starts to increase. With a single stock, a plot with only S would suffice to illustrate this dynamic. However, with S and L moving freely, we must study the aerodynamic jointly in what we call a phase diagram. In this phase diagram, population is on the horizontal axis and the resource stock is on the vertical axis. The green lines represent the combination of S and L, for which S is stable, meaning that S dot equals 0. In the barren island case, S equals 0 and L may have any value. This simply means that without any resources, then the resource stock cannot grow, regardless of the number of people on the island. In the sustained island case, S equals K minus K alpha beta over R times L. If L equals 0, we see that S has to equal K. This makes sense since nobody exploits resources on the island, then the stock will slowly converge to the natural carrying capacity in the long run. Still in the sustained island case, if S equals 0, then L has to equal R over alpha beta. This is the extreme case in which so many farmers exploit the resource that they are always on the brink of extinction. To know how the stock S evolves away from the steady state, we may indicate with arrows what happens when S or L have values different from the steady state. For instance, from the sustained island steady state, if L or S go up, we see from the equation of S dot that it becomes negative, meaning that S starts to decrease. We indicate it with an arrow pointing down. The reverse is true for a decrease of L or S, which leads to an increase in S. Now, these may not all be true equilibria, since they may not correspond to value at which the population is also stable. To know the full dynamics, we now have to study the population dynamics as well. The population dynamics is even simpler than the resource dynamics. The exogenous death rate of the islanders is simply D. The fertility rate is a positive function of harvests, B plus phi H over L. So without any food, we assume that some new islanders can still be born. However, the death rate is higher due to starvation, so B minus D is smaller than 0 and the population shrinks. But as harvest per person increases, this will increase fertility rates. We divide by L since the larger the population, the more moths we must feed for the population to increase even further. The law of motion of L dot, is the net population growth rate multiplied by the number of islanders L. Using the harvesting function, we may substitute H by alpha beta SL. Then we may simplify both L at the numerator and at the denominator. The simplification of L was possible because for a constant resource stock S, there are constant returns to increasing L in terms of harvesting. Simply, a new farmer is a new moth to feed, but he will also produce as much new harvest as the previous one. This is different from the solo model or the Malthus model, in which labor productivity had decreasing returns. Note, however, that this does not mean we may increase population forever, since, as seen earlier, more harvesting puts pressure on resources and eventually will decrease S. This population dynamics, expressing L dot as a function of L and S, and the model parameters, represents the predators in the Lotka-Volterra model. We will now describe its possible steady states and the dynamics around them. The steady state values are again noted with stars. As before, we find the steady states by setting either factors of L dot to 0. The simplest case is L equals 0, corresponding to an island with nobody on it. We may call it the desert island. As for resources, no stock means no increase in stock. The more interesting steady state corresponds to B minus D plus phi alpha beta S equals 0, the sustained island case. This means that if S equals D minus B divided by phi alpha beta, then the population will be stable no matter its size. This is true as long as S star is smaller than K, otherwise the island is simply too small for even a single islander to survive on it. Away from the steady state, if S dips below D minus B divided by phi alpha beta, then the population starts decreasing because each farmer does not produce enough food to sustain himself or herself. If, however, S is higher, then farmers produce enough surplus to allow them to have offsprings, and L starts to increase. In the same phase diagram as before, we show in blue all the possible combinations of S and L for which the population L is stable. It is stable for any S if L is 0. Here S is limited to K, but obviously a population of 0 wouldn't increase even with infinite resources. The sustained island steady state corresponds to any value of L as long as S equals d minus b divided by phi alpha beta. If S goes up, we can indicate that L also goes up, while if S dips below S star, then population starts to decrease. Of course, the only viable steady states are the ones for which both the population and the resource stock are stable. To find them, we will put both stocks dynamics on the same graph. There are a total of 3 possible steady states where the green and the blue lines intersect. One of them may be called the collapsed island, in which both resource stock and population stock are 0, and obviously no growth is possible. A second one may be called the virgin island. Here the nature stock is at carrying capacity K, but no human has yet settled on the island. With no humans to start exploiting, the resource just stays at K. The third steady state is the sustained island. It is a single point at which both K and L are positive and stable. The dynamics around the sustained island is richer since we now have 4 quadrants to consider in which each stock goes in specific direction. The evolution of this situation on the island over time is the sum of the growth of S and L. Note that all arrows crossing the blue line will be vertical since at that point population is stable. Likewise, all arrows crossing the green line will be horizontal since at that point resources are stable. We can already guess that the general movement around the steady state may look something like a circle, but its specific convergence will depend on the specific values of the parameters. To gain more information, we must either use numerical simulations or solve the differential equations explicitly, which may prove tedious for such complex model. This is a summary of the findings. This system of differential equations has 3 steady states: the virgin island, the collapsed island, and the sustained island. To find the exact values of the sustained steady state, simply plug in the value of S in the condition for S dot equals 0, and we find that the steady state population is R divided by alpha beta 1 minus d minus b divided by k phi alpha beta. Similarly, as for the steady state number of boats in the free fishing industry, we find that farming efficiency alpha and the preference for food beta do not mean that steady state population will be larger. Rather, they may also cause islanders to overexploit their island's resources, leaving everybody worse off.